In this video, we're going to present a few examples of what the derivative can represent. And let's just recall what we know so far. So for any function, we know that the derivative represents the instantaneous rate of change of that function with respect to the variable. And that phrase means that we're measuring how much the function is changing based on how much the input to the function changes, right? So this is very much the idea of slope that we've studied in the past, but now we're talking about it not over an interval, but at a point. And that's the idea of the instantaneous rate of change. It's happening at a single point of the function. When we turn our attention to the graph of the function, then we can think of the derivative as the slope of the function at a point. And of course, that's the same as the slope of the tangent line to the function at the point, but we just say the slope of the function. We've already seen one interpretation of the derivative. We saw that if the function represents the position of an object at a given time, x or t, doesn't matter what variable we use, then the derivative represents its instantaneous velocity at that time. And just a quick note, we'll often just say velocity, and that will mean instantaneous velocity. If we want to talk about average velocity, we'll use the whole phrase average velocity, and that will allow us to not always have to say or write instantaneous. So velocity means instantaneous velocity. So I put this information in a table. This is just summarizing what we just said. And our goal in this video is going to be just to add a few more lines to this table. And since we know higher order derivatives now, we can start right away with continuing our physics application. So if a function is position, the derivative is velocity. But if the function is velocity, then the derivative is the rate of change of velocity. And that quantity is acceleration. So the derivative of velocity is acceleration, and let's just go ahead and give that as a formal definition. So we say that acceleration is the derivative of velocity with respect to time. So if we let s of t represent the position function, then we have that the acceleration function is the derivative of velocity, and since velocity is the derivative of position, that makes acceleration the second derivative of position. Okay, so let's work an example using these ideas. Okay, so here's our first example. We have a rocket that is launched from the ground with a velocity of 120 feet per second. It reaches a height given by the position function of s equals 120t minus 16t squared, and that is in feet, after t seconds. And we'll ask several questions about this setup. The first question is, how high does the rocket go? But before we get to that, let's just take a look at the function we're given here. So the position function we're given here follows some patterns that we'll study a little more later in the semester once we learn integration. But I'll go ahead and point out here that the 120 feet per second, the initial velocity, does show up directly here in the function. That's not a coincidence. And then it's important to note that this position function represents a parabola. So this is a parabola with a negative coefficient on the squared term, so it opens down. And notice that there's no constant term, right? So it passes through the origin. So it starts at 0, the object goes up, it comes back down and lands. Here's our vertex. We don't know its formula yet. All right, there's our vertex. And so when we ask the first question, how high does the rocket go? Well, that occurs at the vertex. And then, of course, I guess it's hard to not just review important things. There's an axis of symmetry that runs through any parabola, and the equation of that axis of symmetry is just given by the coordinates of the vertex. So if our vertex is traditionally written in h as hk, then the axis of symmetry is x equals h. Okay, and I deleted that axis of symmetry so we don't overload this graph. We've got a lot to do. So our horizontal axis is t for time. The vertical axis is position, and that's in feet. We can note that our time is in seconds. Okay, so how high does the rocket go? We need the formula for the vertex. Very soon in this course, we'll be able to find the vertex using derivatives, but for now, we don't have that tool, so we'll just use pre-calculus. Remember that the first coordinate, which we've denoted h, is given by the formula negative b over 2a, where we can think of this as a quadratic of this form. So that's what we mean by a, b, and c. Those are the coefficients. And then the second coordinate, which we're calling k, is just a function evaluated at that input. So you really don't need me to do this for you. Go ahead and pause and find the vertex here. Once you do that, go ahead and identify the answer to the question, how high does the rocket go? Okay, so there's the two values, and using the units can help make sure we keep straight what they mean. So it reaches its highest point after 3.75 seconds, and the highest point is 225 feet. So there's the answer to part A. The next question we want to ask is, what are the velocity and speed of the rocket when it's 100 feet above the ground? So let's see, the vertex is 225 feet above the ground, so we can sort of estimate that 100 feet is about right there. But in particular, the rocket hits 100 feet 2 different times. It hits it on the way up and then again on the way down. So we're going to need the times for that happen. We can call that T1, we'll call that T2. But first, let's go ahead and find our velocity function, and then we'll talk about the connection between velocity and speed. Okay, so we know that velocity is the derivative of position. And again, you don't need me to do this. Go ahead and pause the video and find this derivative. Okay, so we just take the derivative of our position function. The derivative of 120 times t is just 120. And the derivative of negative 16t squared is negative 32t. And so now to answer the question, what is the velocity of the rocket at t1 and t2, the points where it's at 100 feet, we need to find the times where it reaches 100 feet. And so we're trying to solve the values of t where s of t is 100, where the position of the rocket is 100 feet. And again, this is not a calculus question. This is a really straightforward algebra question. So here we have a quadratic equation. You can spend, whenever you have a quadratic equation, right, spend about 5 seconds trying to factor it by hand. And if that doesn't work, just go straight to the quadratic formula. So pause here and go ahead and find the values of t that satisfy this quadratic equation. Okay, so just in case it's been a while, here's that worked out. So here I've rewritten the quadratic equation in standard form. Here I've divided by -4 just to make the quadratic formula a little easier to use. Then we have the quadratic formula written out. And then finally we have our simplified exact answer. Since this is an application problem, we're really going to want an approximation. We don't go around saying that the time was 15.5 root 5 over 4. We're going to give something that's a decimal approximation to that number. So even though most of the time in mathematics we want an exact answer, when we're doing application problems, we do usually want an estimate, assuming that estimate makes more sense to use. So for the positive radical, we get 6.545. And for the negative portion, we get 0.955. So on our graph above, the smaller one is T1. The larger value is on the way down. That's T2. We plug those two values for t into the velocity function, and we see that on the way up, the rocket has a velocity of 89.44 feet per second. And on the way down, the velocity is negative 89.44 feet per second. And looking at the graph, those signs, that one is positive and the other is negative, is reasonable. On the way up, we have a positive slope of a tangent line. On the way down, we have a negative slope. Let's see if I can draw it. And then it also brings up an important point that velocity can be negative. We can think of velocity as having two components, speed and direction. Speed is our traditional notion of speed. It's a positive quantity that tells us how fast an object is moving. But velocity also contains a direction. Is the object moving in what we define as the positive direction? And in this case, that would be in the positive s direction, an increasing direction along our vertical axis. Or is it negative? Is it going in the opposite direction? And if you look at the trajectory of our graph, we can see that as the object is moving up, rising towards the vertex, it's moving in the positive s direction, and as it's moving back down towards the ground, it's moving in the negative direction with relation to that s-axis, that vertical axis. So to answer the second part of our question, what is the speed? What is the speed of the rocket? So at both times, the rocket has the same speed, and that's positive 89.44. But on the way down, we say the velocity is negative 89.44 because it's returning back down to the Earth. And the last question for this example, what is the acceleration of the rocket at 100 feet above the ground? Okay, well, we just learned that acceleration is the derivative of velocity, so the second derivative of position, and we found that velocity was 120 minus 32t, so we need to take the derivative of that. Let me switch that 0. And that derivative is simply the derivative of a constant is 0, and the derivative of negative 32t is negative 32. So notice that our acceleration is a constant, and the units for this are feet per second, so we write that as feet per second squared. So the acceleration of the rocket is a constant at any point of the trajectory of that rocket. And in particular, at the 2 times that we found where the rocket is at 100 feet, the acceleration is negative 32 feet per second squared. And you may recognize that quantity, negative 32 feet per second squared, as the acceleration due to gravity. Let's add one more physics application to our table. We won't work an example of this one, but if our function is acceleration, we can talk about the derivative of acceleration. And if you can think of riding on a bus or being in a car, sudden changes in acceleration can create a jerky motion of the vehicle. And so for that reason, the derivative of acceleration is called jerk. All right, let's turn our attention now to some economics applications, and let's see what the derivative is if our function represents the cost of production of an item. If c of x is the function representing the cost of producing x items, then the derivative c prime of x is called the marginal cost of production. So in economics, that phrase, the marginal cost of production, is referring to the derivative of the cost function. That's what it's called in economics. There's an estimate used in economics that I want to explain to you. So we have our derivative as the limit of the difference quotient. So the limit as h goes to 0 of c of x plus h minus c of x all over h. But when we talk about taking the limit as h going to 0, we have to keep in mind that we're dealing with items. So these are objects. And so practically speaking, the smallest value that h can take is 1. So if we approximate the limit of the difference quotient by letting h go to 1 instead of going to 0, we get the following commonly used approximation for the derivative. So we can say that our derivative is approximately, and now the right-hand side as h goes to 1, is c of x plus 1 minus c of x, and the denominator is just 1. And this is commonly referred to as the cost of the x plus first item. So just a little numerical example. If we're looking at c prime of 10, then we get c of 11 minus c of 10. And so this is the cost of making the first 11 items minus the cost of the previous 10 items. So this is approximately the cost of the 11th item. Right, so that's what we mean by the, x plus first item. That's the cost of the 11th item. My of looks like a percent. That might be confusing. So the idea is that our derivative is an estimate of the cost of the next item. And this concept works for costs, revenue, and profit, all of our core economics functions. So here's an example of that. If the cost of producing X cell phones is given by the function 900 plus 80x minus 0.1x squared, find the marginal cost when 250 phones are produced. So the terminology is new, but the derivative concepts aren't. Pause here, see if you can find this marginal cost, and then unpause and check your answer. Okay, so marginal cost just means derivative of the cost function. That's it. And the cost function is a polynomial, so we just get 80 minus 0.2x. And then to find the marginal cost when 250 phones are produced, we just plug in 250 for x. And we see that the marginal cost is $30. And according to that approximation that we just looked at, this derivative should approximate the cost of the 250 first item. Well, let's just check it. Okay, so there's our approximation in red, and just plugging in 250 for x. We just need to find the cost function evaluated at 251. There's our original cost function. And then our cost function evaluated at 250. And when we do that, we see that, so 14,679 represents the cost of producing 251 items. Our 14,650 represents the cost of producing 250. So it cost $29.90 to produce the 251st item, and that was pretty reasonably approximated by our derivative at 250. Okay, so we showed that that approximation is pretty good, assuming that there's no dramatic jumps in our function. Okay, so we can just complete our table by adding marginal cost in the derivative column, and then I'll just remind you that we could replace cost with revenue or profit, and we get the same results.